This time, we are going to talk about the different applications of systems of linear equations. Systems of linear equations arise in a wide variety of applications. First, we can have a set of data points and fit them into a specific polynomial function. This is a process that can be known as mathematical modeling. From a given set of data points, we will be able to create a function, in this case a polynomial function, to predict the behavior of certain tasks, given some data points. We can also use systems of linear equations to analyze networks, and specifically if we have electrical networks, Kirchhoff's law would be a good application of systems of linear equations. And we are going to encounter more applications as the subject or the course progresses. So, first, polynomial curve fitting. Suppose n points in an xy plane. We have x sub 1, y sub 1, x sub 2, y sub 2, x sub 3, y sub 3, until x sub n, y sub n represent a collection of data, and you are asked to find a polynomial function of degree n minus 1. So that would be p of x is equal to a sub o plus a sub 1x plus a sub 2x squared plus a sub 3x cubed up until a sub 1 n minus 1 x raised to n minus 1, whose graph passes through the specific points. The procedure is called polynomial curve fitting. So this would mean we are going to look for a function, and in this specific case a polynomial function, that would contain all of these points in the graph of the function that we are going to look for. Or in other words, these are solutions of the polynomial function that we're going to look into. Now, if all the x-coordinates of the points are distinct, then there is precisely one polynomial function of degree n minus 1 or less that fits the n points. So if all the x-coordinates are distinct, then there will be only one polynomial function. This is a characteristic of functions in general. So to solve for n coefficients of p of x, we substitute each n points to the polynomial function and obtain n linear equations in n variables, a sub 0, a sub 1, a sub 2, a sub 3, up until a sub n minus 1. So, after plugging in the points, we then plug into our matrix or to our system of linear equations and then solve for the values of the coefficients of our polynomial function. So, let's have a specific example. We are asked to find a polynomial function that fits the points 2, 5, 3, 2, and 4, 5. Now, we have here 3 points. That means the polynomial that we're going to look into would be of the second degree. N, this is the number of points, minus 1, 2. So that will be a degree of 2 or a quadratic function. And a quadratic function has the general form y is equal to ax squared plus bx plus c. What we're going to do now is plug in these values into this function. And how do we do that? Remember that an ordered pair is of the form xy. So we replace the x coordinates in the x, and we replace the y coordinates in the y. For example, if we plug in 2, 5 here, we're going to have now 5 is equal to a times 2 squared plus b times 2 plus c. If we are now to plug in 3, 2 into our equation, we're going to have now 2, our y coordinate, would be equal to a times 3 squared, our x coordinate, plus b times 3 plus c. Finally, plugging in 4, 5, we can have 5 is equal to a times 4 squared plus b times 4 plus c. Now, we can rewrite the system more efficiently as 4a plus 2b plus c equals 5, 9a plus 3b plus c equals 2, 16a plus 4b plus c equals 5. And then we solve the system that we have formed for the values of a, b, and c, which would be the coefficients of the polynomial function, in this case quadratic, that we are going to look for. So, we are going to solve the system using matrices, hence we shall write our system in augmented matrix form. So, our augmented matrix M, I will just label it as M, will have the following: 4, 2, 1, 5, 9, 3, 1, 2, 16, 4, 1, 5. Now we can apply either Gaussian elimination or Gauss-Jordan elimination to solve for this system. Now what I will be applying will be the Gauss-Jordan elimination, so we can already get the values of A, B, and C by getting its reduced row echelon form. Now, the actual process of the Gauss-Jordan elimination will be left to the viewer. Finding the reduced row echelon form of our matrix M will be as follows. Reduced row echelon form would be this specific matrix: 1, 0, 0, 3, 0, 1, 0, negative 18, 0, 0, 1, 29. So, given this reduced row echelon form of our augmented matrix, we can now say that A is equal to 3, B is equal to negative 18, and C is equal to 29. Therefore, the polynomial function we're looking for that would fit the data points 2, 5, 3, 2, and 4, 5 would be y is equal to 3x squared minus 18x plus 29. And that is an example of polynomial curve fitting.